Okay, so a body of mass 12 kilograms is moving on a line of greatest slope of a rough plane inclined at an angle of 20 degrees to horizontal under the action of a constant force of magnitude 150 newtons acting up the slope. Okay, the coefficient of friction between the body and the slope is 0.6. So I've started to draw the diagram here, okay, and that's what you need to do essentially, right? You have to draw a diagram here, nice and clear, nice and big, okay? It's not 100% clear here whether it's moving up or down the plane, okay? We're going to be able to work that out mathematically, easily enough. But because it sort of says these words here, under the action, okay, it moves under the action of a constant force of magnitude 150 newtons acting up the slope, we can sort of assume that it is going to be moving up, right? So mathematically we'll be able to prove that now anyway, because if that's the case, our acceleration, when we calculate it in A, should be positive, okay? Now let's draw all the forces in then, right? Super important that we get this correct here. Now we'll start off with the normal reaction, okay? Which is, remember now, is perpendicular to the plane, okay? And what you should do then, remember, is have a dotted line then going this way, broken line going that way for our y-axis. Okay, so we put R here. Okay, and then we've got our nice y-axis there, yeah? Okay. Now, we also need to put the x-axis in here. Okay, so we've got the force of 150 newtons going up the plane, and then, of course, the broken line going down the plane here then, okay? Okay, so we can put the weight component in. So we've got here 150 newtons. Okay. Now the weight, remember, okay, acts vertically downwards. Okay, so it's important that you do get this looking vertically downwards here. Okay. And then we can have the components then in the y-axis and the x-axis. So this object here is of mass 12 kilograms, so the weight is 12 g. And remember then, if this is 20 degrees, this is also 20 degrees here as well. Okay, so when I turn it around to make my cross, the y-axis first then, because the angle here is contained on this side, so this will be cos, so it'll be 12g cos 20, and then perpendicular to it, okay, in that direction, be 12g sine 20. Okay, good. So there it looks like we've got all the forces in, apart from one other force. Okay, this time remember it's a rough plane, so we need to put the force of friction in as well. Okay, now remember about friction, it will always oppose the direction it's going in. So because we know it's like moving up the plane, okay, friction will resist it, so friction will act down the plane. Okay, so I need to draw a friction force in there, okay, and we'll call that FR for friction. Okay, so don't forget about that friction there. Fantastic. Okay, so let's resolve then, okay, in A, right? Well, if I resolve perpendicular to the plane first, okay, so instead of writing perpendicular, resolving perpendicular, I'm just going to do that, okay, to show perpendicular to the plane. While looking at the cross system there, remember then R will equal 12g cos 20. There's no movement perpendicular to the plane. It always stays on that x-axis, okay, no vertical movement in the y direction. So R will equal to 12g cos 20. Okay, so we can leave that like that for a minute. Let's then resolve parallel to the plane. So going up the plane. So remember now, when we resolve parallel to the plane, we're going to apply Newton's second law, okay, in the direction of motion. So the resultant force equals to mass times acceleration. So we've got 150 newtons pulling it up. Take away then, well, remember now, think about what's resisting it. First of all, you've got the weight component, haven't you, pulling it back. Okay, when you're moving up a plane. but also you've got the friction. So in this case, you've got to take away that as well. Okay, so it's quite a long sort of equation here, because you're taking away two resistant forces, the weight component and the friction. That will equal then to the mass, which is 12, times the acceleration. Now, to work out acceleration, I need to know what friction is, and friction is really easy. Okay, so the friction max value, remember, will equal to mu r. So the friction in this case, well, mu they say is 0.6, says in the question, and r is this here. So 12g, 12 times 9.8 times cos 20. So I work that out on my calculator. I get 66.305 newtons. Okay. So I've got friction. All I've got to do now is plug it in there, and I can get my acceleration. So if you want to call this, we can call these all these equations if you want. Let's just call this star here. Okay. So sub, you call them 1, 2, 3 if you want. Sub in star 150. Take away 12 times 9.8 times sine 20. Take away friction, which is 66.305 equals then to the mass, which is 12a. So I'm literally going to type all that in one go. On the left hand side, then I get 43.47 etc. equals 12a. So then I just got to divide by 12 to get my answer for a. So answer divided by 12, 3.62 meters per second squared. Okay. In B, then it says state one modelling assumption you have made in your solution. Well, think about this here. We've got the resistance of friction, but if you've got a big object, there'd also be air resistance, wouldn't there? Okay. So there'd also be a resistant force due to the air. Okay. So we've ignored that. In order to ignore it, we need to model the object as a particle. Okay. Model it as a particle. If you model it as a particle, it has no dimensions. Okay, there's no bulkiness to it. It's just a dot. So modeling it as a particle, that will mean we can ignore air resistance. Okay, so make sure you put that down there, that you modeled it as a particle, and then the resulting effect is that we can ignore the air resistance.